Hello learners, welcome to session 6 of unit 4, Infinite Continuous Fractions. I am Unkaila Dasmani, your course instructor for this course. As we mentioned earlier, that continuous fractions provide tools that yield powerful algorithms for solving problems in number theory. In this session, we look at infinite continuous fractions, which represent irrational numbers. By the end of this session, you should be able to express an irrational number in the form of a continuous fraction. You should be able to determine the approximation of irrational fractions and also state the applications of infinite continuous fractions. Definition of a continuous fraction. So in this session, we will not assume that ai is an integer and ai is greater than 0 for I greater than 1. And the expression may go on indefinitely. So if a0 up to a3 is any infinite sequence of positive integers, then the sequence of Cn, that's a0 up to infinity, converges. More generally, if an is an arbitrary sequence of positive pairs such that the summation of n equals to 0 up to n equals to 0 up to infinity an. As an diverges, then cn also converges. So as we affirm that continuous fraction is an expansion of the form, and we've already looked at this expansion of this continuous fraction. Okay, so I think we have already gone through this. Just recall, a revision. We've already done this in the previous lessons. Okay, and I think you still remember finite continuous fractions. Now let's look at the infinite continuous fraction, and I've already given you the definition, and the expression over here is what we discussed in the previous lesson. So this expression, in which ai is a real number, may converge or diverge depending on certain conditions. So what is then the difference between convergence and divergence of set or series or sequence? Okay, so let's look at example 33. Write the irrational number 1 plus root 5 on 2 as a continuous fraction. Okay, so let's see. We can write 1 plus root 5 all on 2 as 1 plus, let's say minus 1 plus root 5 all on 2. And I hope you agree with me. Okay, so once you're able to write it in this form, and you can see that it is same as a0 plus t0 plus t0. So in this instance, what can you say? You can say that your a0 equals 1, and then your t0 equals minus 1 plus root 5 on 2. That's our t0. And what is the next one? We repeat the process, so we find 1 on t0. So 1 divided by t0 is actually 1 over that expression. 1 over this expression. Let me underline with right line. 1 over this expression. And what do we get? 1 over this expression, we get you get 1 over that, you simplify, you rationalize, and then at the end of the day we get the answer to be 1 plus root 5 all on 2. So you get the same thing backwards. And after here, what do you see? Then you can get your a1 equals to 1, your t0 equals minus 1 plus root 5 all on 2. So when we proceed, the process will continue in that order, and it will never end. it means that you get your a1 equals 1, a2, let me start with a naught first. A naught equals to 1, a1 equals to 1, a2 equals to 1, up to the last term, and that last term will be what? It will keep on going, which it will not end. In that order, we can therefore write 1 plus root 5 all divided by 2 as 1, 1, 1, 1, keep on going, which it will not end. Okay, so if actually look at the solution to this question, let's look at the next section. So here we want to look at approximation of yi. Oh, this one is just simple, and I've already talked about that. So go through your course material. It is there. You can write some of the approximation of yi over there. Then I want to look at another approximation of the pi. Oh, that one too is simple. Just find few partial convergence there. You can do it yourself. So go through. That is as an assignment. Okay, let's prove the irrational number root 2 as a continuous fraction. So we want to do that. So you have so many ways you can do. Let me see if I can think of using the conjugates by something like that. So if I write root 2 minus 1 multiplied by its conjugate, that's root 2 plus 1, what do I get? The answer is 1. I hope you agree with me like that. Okay, once you agree with me like that, then there's so many interesting things we can deduce from here. So from here, if I decide to make root 2 minus 1 the subject, I'll get 1 divided by root 2 plus 1. I hope you agree with me like that. Let me call this equation 1. Okay, so from equation 1 here, what can we see? I think we can make root 2 the subject. When I make root 2 the subject here, what do I get? I'll get 1 plus 1 divided by root 2 plus 1. I hope you agree with me. Okay, let me call it star. After here, that means that we can have so many interesting things we can deduce from here. Let me put equation star into equation 1. Wherever I see root 2, I write this root 2 there. I place that root 2 here. So that is root 2 minus 1 is actually equals to 1 divided by, there's 1 here already, so you know addition is commutative. I can write 1 plus root 2, and 1 plus root 2, I'm going to write equation star there, plus 1 plus 1 divided by root 2 plus 1. Okay, and I think you agree with me like that. And this is the same as, what do I get? 1 plus 1 is 2 plus, oh, let me write the whole show so it becomes very simple like that. Let's see, and this equals to 1 divided by 1 plus 1 is 2 plus, I'm going to put root 2 here, plus 1 divided by root 2, so going to be that repetition, plus 1 divided by root 2 plus 1. Then I put root 2 over there. At the end of the day, what do I get? I get 2 again, plus 1 divided by, I put the root 2 still there again, so I get 2 plus 1 divided by, so 2 in that order, so it gets up to infinity. So if I make this 2 here, the 1, let me use the color to indicate root 2 minus 1. If I let the 1 here cross, let's say I subtract 1, I add 1 to both sides, adding 1 to both sides, so you get root 2 is equal to, okay, let me clean that one here, then I can make root 2 is now equal to 1 plus 1 on 2 plus 1 on 2 plus 1 on 2 plus 1 on 2, and that keep on going, which will not end. In that order, we can say therefore root 2 equals 2. That is the first one, is as a continuous fraction. The first one is what? The first one is 1, that is 1 here, and the next one is 2, 2, 2, up to infinity. So the last one will be 2. Keep on going, 2, 2, 2, 2, 2, 2. So we've shown that root 2 is a continuous fraction. It's an actually infinite continuous fraction. Good.